to have University of California and Irvine, and we will talk about the variational theory.
Okay, thank you so much, Nader, for the introduction and invitation. It's really a pleasure to be here today. It was like almost a dream to meet Professor Masmoudi and learn from him. So I'm happy that this wish came true finally. I'm very excited to share with you our new line of research that came out first in this paper, GFM 2022. And because it was addressing a basic problem in aeronautics, it got some attention. It was the most downloaded paper in GFM 2022 and the second most downloaded paper this year, 2023. So we're happy that it's getting some attention. And let me just try to motivate this talk by quoting from Ken Chang's article in New York Times. He said, to those who fear flying, it's probably disconcerting that physicists and aeronautical engineers still passionately debate the fundamental issue underlying this in the what keeps planes in the air. So hopefully no one is flying soon to get scared. But I mean, the claim that we're putting forward here is that the current theory of flight that we teach throughout the world to our undergrads is quite fragile. And let me show you why. So here is the problem that we're trying to solve. Here is a two-dimensional airfoil, and we want to compute the lift force. This is the simplest problem in aerodynamics. It can't be simpler than this. It's not a wing, it's not an airplane, it's just a two-dimensional airfoil. And you know, we engineers or applied mathematicians or physicists, we always like to go back to fundamentals, governing equations. If we can solve Navier-Stokes, so let's look at Euler. Here is Euler, steady. And if you give me a legitimate solution of Euler, any solution you like, you go and try to solve Euler and give me a legitimate solution. So it satisfies the PDEs and the boundary condition. So it's a perfectly legitimate solution of Euler. I can always construct a special flow field U1. It's not a solution of Euler, but together with U0, this is like a small lemma. Together with U0 plus gamma times U1 is a solution of Euler problem for any value of gamma. So a solution with gamma equals 1 is as legitimate as a solution with gamma equals 1 million. Both satisfy the partial differential equations and boundary conditions. They are perfectly legitimate mathematical solutions. So the question is, what does gamma represent? Maybe it's not important to worry about. Actually, gamma represents the circulation over the airfoil, which solely dictates the lift force. If you give me gamma, I immediately give you back the lift force. Rho is the speed and U is the free stream velocity. So it solely dictates the lift force. So ironically speaking, Euler equation alone cannot determine one of the most fundamental quantities in flight, which is the lift force. It's the most important quantity that we care about. The question has always been, what solution does nature select out of this infinitely many possible solutions? So, you know, it's as if you have x squared equals 4, so I have x equals plus or minus 2. So let's look at these solutions and pick the one that matches the physics more, the most physical one. So let's look at these solutions. Here is a solution with small value for gamma, so the corresponding lift is small because lift is proportional to gamma. Here is another solution for a larger value of gamma, and the corresponding lift is large because, like I said, lift is proportional to gamma. So for both scenarios, the flow, because we have a sharp edge here, the flow goes around the sharp edge from the lower surface to the upper surface here, and vice versa in this example. And you know, rotating around the sharp edge is like you're driving your car and you do a steep turn with a zero radius of curvature. This, you know, requires an infinitely high centripetal acceleration, infinitely high curvature. We call it a singularity. Nature, I mean, most likely it doesn't do that. So here is actually the preempted flow visualization 1904 with water channel, steady flow over airfoil. It doesn't do that. The two flows come smoothly at the trailing edge. So here comes the role of the infamous Kutta condition, or you want to say Kutta-Joukowski condition. So they said, okay, we gonna pick, you know, luckily there is one solution only out of this infinitely many family. There's one solution that mimics what happens in nature. So this seems to be the right solution where the two flows come together nicely, no singularity at the edge, and the corresponding gamma and lift must be the correct one that nature provides to us. So this is the Kutta condition. It simply says that the circulation and drift are such that there is a smooth flow of the sharp trailing edge. There is no flow around the sharp edge from the lower surface to the upper surface or vice versa. And this is how we teach aerodynamics to our undergrads throughout the world. And this is the theory, the dominant theory that is discussed in every single textbook in aerodynamics. But you know, the question that luckily our undergrads do not ask, I did not ask when I was undergrad, that what happens with this shape? There is no singularity to remove. All solutions are bounded. All solutions are perfectly legitimate from a mathematical perspective. We don't have any means to pick a single solution out of this family. So the dominant theory that we teach all over the world immediately collapses. There is no theoretical model that can predict lift over this shape. You need to go and solve Navier-Stokes equation. Good luck. Not only this shape, even if you have multiple sharp edges, so there is one solution that is smooth at this edge, but not necessarily the other, and vice versa. So which solution should we pick? The ambiguity remains. And not only that, even for our usual shape airfoil with a single sharp edge at the end, but you have a fast maneuver, like an unsteady flow, a fast maneuver like those done in the Top Gun movie. So first of all, Martin Kutta never claimed that his condition applies to unsteady flows, and indeed it doesn't. Here is Prandtl flow visualization in the exact same catalog of picture. This is a step change in the angle of attack during the transient period before reaching steady state. You see the flow goes around the edge from the lower surface to the upper surface. So you have the starting vortex kind of thing. So the Kutta condition doesn't seem to be applicable in unsteady flows, and you have like tens of papers in the literature criticize the application of Kutta condition to unsteady flows. Yet the entire theory of unsteady aerodynamics, from the pioneering work of Wagner, Theodorson, von Karman, and Sears, all the way to the most recent work in the JFM, they all adopt the Kutta condition in their unsteady models, because simply there are no alternatives. If you don't have the Kutta condition, there is no means to single out one solution out of the family. And this actually, so this is why I'm claiming that the current theory that we teach to our undergrads throughout the world is quite fragile. If you change something in the shape of the wing or in the flight condition, the theory collapses, and we don't have a means to compute the lift force, which is very important.
What is the Kutta condition again?
This is the Kutta condition, is that it removes the singularity. Any other solution, the speed and acceleration goes to infinity. This is the only solution where the speed is finite. So if you have a sharp edge, it helps you to remove the singularity. But if you don't have a sharp edge, there is no singularity to begin with. So there is no way to single out the solution. Okay, so this actually led to the following. If you have Euler, but is not sufficient to determine lift force, but then if you solve Navier-Stokes, I mean, we cannot solve Navier-Stokes analytically or even numerically on a high-density number. So, but if you accept an approximate numerical solution of Navier-Stokes, you'll get a good value for the lift that matches reality. So this picture on its own seems to suggest that lift is due to this added term. Lift is due to viscosity, due to friction. And when we feed Euler equation with a Kutta-like condition, we get lift that is close enough to Navier-Stokes in the nice case attached flow case. So this also seems to suggest that the Kutta condition is a viscous condition, particularly because Kutta condition was based on observation from reality, and reality is viscous. So this is I would say, the conventional wisdom in the aeronautical engineering community. Like, pick your favorite aerodynamics book. Here is Anderson. It says, nature enforces the Kutta condition by means of friction. Here is Professor Ackroyd of Manchester. We fly courtesy of the air's very small viscosity. That's the accepted wisdom in the community. Viscosity gives us lift. And the issue is deeply rooted in D'Alembert paradox. Because D'Alembert, around that time, he solved ideal flow equations over some shape like this. And he obtained a completely symmetric solution, fore, aft, up, and down. So it's resulting in a zero net force. And the issue is that D'Alembert solution, if you try to replicate it over any shape, not necessarily this one, any shape, it will give you a zero force. So deep down in the background of most, not all, most physicists and fluid mechanicians, ideal fluids are forceless. They cannot lift an airplane. They cannot produce forces. So just before leaving this slide, there is one fact that I'd like to stress is that around that time, we really did not know that Euler equation, steady two-dimensional, or unsteady, two-dimensional. We really did not know that Euler equation two-dimension has infinitely many solutions. And D'Alembert zero force solution is only one solution in the family. So we're not sure whether nature selects D'Alembert solution all the time or not. The situation was exacerbated even more with this very interesting work at Caltech in the 50s. So they wanted to settle this debate. So they said, okay, if I am claiming that this bag is heavy because there is a box inside that is too heavy, it's making the entire bag heavy. How to test this hypothesis? So remove the box and see if the bag is still heavy or not, right? This is what they said. This is what they did. They said, okay, let's remove viscosity and see what happens. So let's cool down helium-2 down to crazy temperature like 2 Kelvin. It becomes a super fluid. Now it has zero friction. So they made a super fluid wind tunnel. This work was done under the guidance of great names like Feynman, Liebman, and Roshko. So they made a super fluid wind tunnel, very small wind tunnel, where a super fluid is flowing over some shapes. And they measured the lift. Do we get lift or not? They actually got zero lift. So this was their conclusion. The classical viscosity boundary condition at the trailing edge, i.e. the Kutte condition, doesn't apply. So they are calling the Kutte condition a viscosity condition as usual. So, and this made sense. So lift, we get it from the Kutte condition. We believe that, or they believe that the Kutte condition is viscous. Here we have an experiment where no viscosity. So we found that the Kutte condition doesn't apply and we didn't get lift. It made sense and it was like, that's it. That's the experimental stamp. Lift is due to viscosity. Just one thing before leaving this slide, they tested only symmetric shapes. Purely symmetric shape, 4 aft, up and down, flat plate and an ellipse. They never tested our usual aerofoils or any asymmetric shape. Okay. So anyway, that's the background. Let me tell you our own version of the story. Okay, that's the background of this. No. This is what we're supposed to solve. Navier-Stokes, which is dynamics, nothing but force equal mass times acceleration, and then subject to some kinematic constraint of continuity. What we actually solve in potential flow is this guy, right? This is what we teach on the undergrad. And this is a composition of two equations, the continuity constraint and irrotationality assumption. And nothing here says force equal mass times acceleration. They seem all kinematics. So it seems that potential flow is purely kinematic and there is no dynamical consideration, which means that if we want to generalize the Kutte condition, we're not criticizing the Kutte condition. It's so invaluable in aerodynamics, but its region of applicability is so confined. We want to generalize it. So we want to have a general theory. Okay. If we want to generalize the Kutte condition, it means that the generalization must come from dynamical consideration, force equal mass times acceleration, because this is what is missing, right? But that's very challenging. How to project the dynamics, Navier-Stokes or Euler, doesn't matter, on one-dimensional manifold to focus on gamma alone. I don't want to go and solve the entire flow field down to the Kolmogorov length scale. I'm happy with my model. All what I want is one single parameter gamma. Can you give me gamma? That's it. So that's a very challenging problem. How to project the entire dynamics on one-dimensional manifold. So here I'd like to go and remind you, this is a standard slide from a graduate course in analytical mechanics. We can do dynamics in one of two ways. There is the Newtonian way, force equal mass times the acceleration. There is the variational Lagrangian way. Okay. And just to bring everybody up to speed, I'll give an example on how to solve a problem using either approach. Like, let's consider this example. I have 1,000 particles in 3D space. So we have 3,000 degrees of freedom. But they are not all free. They are rigidly constrained. Okay. So I'm removing many, many degrees of freedom. Let's assume that at the end, we have only 2 degrees of freedom. Okay. That's the example that we have. how can we solve this using Newtonian mechanics? Well, the very first step in Newtonian mechanics is to draw a free body diagram. Right? So I have to isolate each particle and write down the equation of motion for each particle. So these are 3,000 equations of motion. And I need to be patient enough to mathematically manipulate them to arrive at two relevant equations at the end. Because at the end of the day, I have only 2 degrees of freedom. So that's the only way to do it using Newtonian mechanics. There is no other way. I have to write down 3,000 equations of motion and solve them, even though I have 2 degrees of freedom. On the other hand, I mean, this is actually for a continuum of infinite fluid particles, you have a partial differential equation. Right? So you have Euler or Navier-Stokes. On the other hand, when we look at the Lagrangian variation, there are many ways to describe it. I'll describe it in my own way, which is sometimes controversial, but you know, it's I'll do it anyway. So the main premise is that nature minimizes a certain fundamental quantity. So any motion, it's you know, you have an orbit or a planet that is orbiting the sun, or a tree leaf falling to the ground, or a heart that is bumping, or a viola string that is vibrating. They all move such that a certain fundamental quantity that is minimized. So if you manage to write down your fundamental quantity in terms of your degrees of freedom, then the rest is easy. It's high school calculus. Differentiate and equate to 0. You get 2 equations directly in the 2 unknowns without the need to solve 3,000 equations. So whenever you have a constraints, this approach is much better, much more efficient. And the interesting thing is that they are equivalent. So we always have respect to first principles in mechanics, like Newton's equation. These are also first principles in mechanics.
Aren't Newton's equations extrema of the action?
Yeah, exactly.
Not minimum.
Yes,
Extrema.
exactly. Yes. And I'm coming to this. Yeah, but that's a very good point. I'm coming to it. So it seems that this approach, though, is more suitable to our problem. Why? Because if the classical theory is giving us the velocity field everywhere, I know you at any x, but there is only one unknown parameter, gamma. Then if I can manage to write down my fundamental quantity in terms of gamma, I will differentiate and equate to 0. I'll get 1 equation and 1 unknown, and I'm done. So what is the quantity that nature minimizes? Well, I mean, in most of the classical textbooks, it's the kinetic energy, or kinetic minus potential. This is incompressible, so it's kinetic energy only. So fine, I mean, I have u here, I plug it there, I integrate over the space. The result is just a function of gamma, and I differentiate and equate to 0, and we get 0. That was quite disappointing. So it's a non-trivial question to ask. What is the magic quantity that nature minimizes in every nice and attached airfoil problem? We managed to solve this, or to answer this question, when we learn about Gauss' principle of least constraint. So Gauss wrote this paper, a few pages paper, like 3 pages, almost no equations. It's full of text and wisdom. And then Jacobi turned this text and wisdom. Yes, please.
So what is the interpretation of the fact that minimizing the kinetic energy implies no lift? Like this is a true statement that we have proved, right? So what
To statement that
a true statement that we have proved that minimizing the kinetic energy ends up giving no lift. So what is the physical interpretation of it?
I mean, before the next slides, up to here, I can give you the, oh yeah, this makes sense, because this neglects viscosity, and viscosity is the root. Okay, but it turns out, no, let's see why. Yes, so it's here is Jacobi. Jacobi turned this few text or few pages text into something mathematical that someone, an engineer like myself, can use. If you have a collection of particles, doesn't matter how many, here is the equation of motion of each particle. In analytical mechanics, we typically decompose forces into 2 categories. There is the applied forces in green that you apply yourself, and there is the constrained forces in black. The constrained forces are there in nature only to enforce a given constraint. If there are no constraints, no R. If the constraint is removed, R will no longer be there. Let me give you an example. Here is the pendulum. The mass of the pendulum is constrained to move along a circle. So there must be a force whose sole role in life is to ensure this circular trajectory constraint. That's the force in the rod. So the force in the rod is classified as a constraint force. And here is another example, a mass rolling over an incline, the normal force is a constraint force. As you can see from these simple examples, constraint forces are usually normal to the motion in some sense. So they don't produce work, they are workless, okay? Okay, after learning this, here is Gauss' principle. It says that the following quantity must be minimum at every instant in time. And this quantity has a meaning. It actually makes sense. So let's look at that. So F is the applied force divided by mass is the applied acceleration, applied motion, the motion that you want. I want to move in this direction, so I apply a force in that direction. A is the actual motion that you're gonna get at the end. In the absence of constraints, so there is no R, these two quantities are exactly the same. You apply a force, you get a motion in the same direction. In the presence of constraints, however, if you have non-zero R, the actual motion will deviate from the applied motion. Why? Because of the constraint. Then it means that it will deviate from the applied motion only by the amount that satisfies the constraint and not anymore. So this is why this quantity must be minimum. And in fact, you can rewrite this quantity from the equation of motion as R over M. And it's as if we're minimizing the summation of all constraint forces. So this is why, or hence the name least constraint. Okay. And when you write it as R like this, it looks familiar. It looks like a residual. R is really a residual between the applied motion and the actual motion. So it's as if we're minimizing the residual square. So brings the bill of least squares. And actually, least squares was developed by Gauss himself. This is his own words. It's quite remarkable that nature modifies free motions incompatible with the necessary constraints in the same way in which the calculating mathematician uses least squares. So he's saying, so inspired by his own method of least squares, he's saying that nature solves a least squares problem at every instant in time. This is his view. Gauss' principle is not commonly known. I was teaching analytical mechanics for 10 years. I never heard of it, unfortunately. So I heard of it only when I read in the history. Actually, this is the words of Papastavridis. He said, in most of the 20th century English literature, Gauss' principle has been barely tolerated as a clever, but essentially useless academic curiosity when it was mentioned at all. It wasn't until the efforts of Edwardi and Kalaba, they revived it in the world of robotics. Our main contribution is to apply it to fluid mechanics. I'm going to show it in the next slide. But before leaving the slide, I'm going to give a fun fact. I was very happy when I learned that there are only 10 names between Gauss and myself, thanks to Haithem. And there are some nice names here like Klein and Hilbert. So anyway, let's go back to your point. Let's make a comparison because this is very well known. Hamilton's principle of least action versus Gauss' principle of least constraint. And this actually makes our way of selling things along this line of research difficult, because whenever I use variational principle, people immediately jump to here. First of all, if you look at the dates, they were developed around the same time. Yet this is very famous. It's discussed in every single textbook in analytical mechanics and classical physics. This one is rarely encountered, which is quite interesting. The applied forces here in Hamilton's principle of least action, they must be, I mean, I don't want to get into details. Let's say coming from a potential energy, conservative kind. So here, no, they can be arbitrary, which is a big plus. That's really a big plus. Principle is stationary. It's not necessarily minimum. All what we know is that first derivative is zero, first variation. Gauss' principle is a true minimum. That's also another big plus. Hamilton's principle, the quantity that we minimize or whatever extremize is an integral over time, integral of the Lagrangian, right? Integral of kinetic energy or whatever over time, the action. So your variable that you're differentiating with respect to is the whole trajectory. So this needs a special calculus, the calculus operations. And when you use calculus operation, you get Euler. Here, no, Gauss' principle is instantaneous. It is applied at every instant in time. So we don't need calculus operations, just a regular ordinary calculus, high school calculus. You differentiate with respect to generalized acceleration. The right acceleration is such that it minimizes this quantity at every instant in time. So the dynamic system evolves from one time to another instant to minimize this quantity. That's the philosophy of Gauss, and this order necessary condition here is principal virtual order. So it's equivalent to Newton's equation in some sense. There are other differences, but I'm going to skip for the case of time. Maybe we can come back later. There is a special case of Gauss that I'd like to mention also. In the case of no applied forces, if you don't have applied forces, so your equation of motion is just, you have forces, reaction forces only, or constraint forces only. In this case, your quantity is simply mass times acceleration squared, and this has a name in mechanics. It's called the aphelion. And you can actually prove that if you're minimizing acceleration squared, it's equivalent to minimizing normal acceleration squared. And this is a special case of Gauss principle in the case of no forces. It's called Hertz's principle of least curvature. And it has its own philosophy, which makes perfect sense. If you have a particle, no forces, it moves along a straight line, right? So this is Galileo or Newton's first law, or whatever you want to call it. So no forces, the particle moves along a straight line. But if it's constrained, it has to deviate from the straight line. Why? Because of the constraint. Then it will deviate from the straight line only by the amount that satisfies the constraint and not anymore. And the deviation from a straight line is curvature. This is why the name least curvature. Okay. So a particle moves according to least curvature. A collection of particles moving, they move such that the total curvature in the system is minimized. And that's a special case of Gauss. I think that's enough. Let's go and apply it to fluid mechanics. Incompressible flow, of course, here. So this is Navier-Stokes, mass times acceleration equal forces, and I'm taking unit density, unit mass, because it's incompressible. In order to apply Gauss or any analytical mechanics, any variational principle, I need to classify forces into applied and constrained forces. Viscous forces are applied forces. They are not associated with a given constraint, so that if the constraint is removed, they will no longer be there. This is not the case. They are part of the fluid identity, so they are applied forces. Interestingly, as many people know, particularly the math community, this is very well known, perhaps less well known in classical fluids community. Pressure forces for incompressible fluids is a constraint force. Actually, its sole role is to enforce the continuity constraint. And it's so easy to show in a couple of lines that if you have a field, a velocity field that satisfies continuity and no penetration, boundary condition, then the pressure force doesn't do any work on it. It's worthless, which comes from the Helmholtz-Hodge decomposition. That if you have a velocity field, you can decompose it into two components, one that is divergence free, and the other one is the gradient of a scalar function. And these two components are orthogonal. So the velocity field U is not only orthogonal to the Nabla pressure, it's orthogonal to Nabla of any scalar function. And let's sketch this. Let's sketch it. So this is R3, our wallet, and here is a blob of fluid. Okay, so it goes after some time into another configuration, and phi t is the flow map that maps the initial configuration to the final configuration at some time. Phi is a smooth map with a smooth inverse. So the mathematicians, they have a fancy name, which is a diffeomorphism, right? But for an incompressible flow, it's volume preserving, right? So it's a volume preserving diffeomorphism. Okay. Now let's go to this fictitious space, infinite dimension space, very large space, the space of all these diffeomorphisms. So any point in that space is one of these maps. Okay. So any point here is a snapshot of flow field. Why? Because this map maps all the initial conditions to this snapshot. Okay. Not all points here are relevant for an incompressible fluid, because only those lying on the volume preserving surface or manifold are relevant. A curve here is just a flow field, right? An evolution of a flow field. And the tangent vector to that surface is just a velocity field that satisfies continuity. It's a divergence-free velocity field. By Helmholtz-Hodge decomposition, the pressure force is normal to that surface, right? And now look at this picture and use basic knowledge in mechanics. Let's consider ideal fluid. For ideal fluid, you don't have viscosity. The only acting force is pressure force, right? But the force is normal to the surface. So on the surface, the fluid is free. No force is on the surface. And like any free mechanical system, The least action says it has to move along straight line, along geodesics, right? This is exactly Arnold's seminal result, but in a sketch way that the motion of ideal fluids are geodesics in the space of volume preserving the human physics. Okay, so that's natural. Now let's take one step ahead. Let's now consider real fluids with viscosity. So I have other forces coming from viscosity. And let's, instead of applying least action, let's apply Gauss least constraint. What does Gauss say? Gauss says that, well, this force is a constraint force. So the summation of all constraint forces is minimum. That's precisely what we're saying here. That the total magnitude of the pressure gradient over the domain must be minimum at every instant in time. And this is what we call the principle of minimum pressure gradient. Okay. So I walked you through how we came up to this conclusion, doing nothing but applying Gauss principle verbatim. But here is a theorem that which is not fancy at all. It's applying standard tools in calculus operation. It says if you give me a solution that minimizes this function is a minus f over n, which is nothing but the pressure gradient, subject to continuity for all time and space, and the no penetration boundary condition for all time. This can be anything, it doesn't have to be homogeneous. Then this solution must satisfy Navier-Stokes equation. And again, this is really standard tools in calculus operation. It's nothing fancy. So it means that the Navier-Stokes equation is the necessary condition for minimizing the pressure gradient, which turns a fluid mechanics problem into a minimization problem. Why? Because if you give me a solution that minimizes this thing, it is guaranteed to naturally satisfy Navier-Stokes. You don't need to worry about Navier-Stokes. In fact, this minimization is a bit more general than Navier-Stokes in the following sense. If you have extra forces like electromagnetic forces, for example, if I have electromagnetic forces, I must come here in Navier-Stokes and add my force. I must modify the equation. Whereas the PMPG that applies verbatim with the exact same statement, the total magnitude of the pressure gradient must be minimum at every instant in time. So we use this to solve classical fluid problems without going to Navier-Stokes, just minimize the pressure gradient. So for example, this is Stokes' second problem. I have an infinite plate that is oscillating back and forth, creating an oscillating boundary layer. And this is the standard, form of solution in the textbooks. It's a model representation for the x velocity and y velocity 0. This form naturally satisfies continuity. So continuity is taken care of. Now, there is no way to determine these things without dynamical considerations, like force equal mass times acceleration. So if you go to Navier-Stokes, it will give it to you. Okay? That's the standard solution in the book. Here we don't go to Navier-Stokes. We plug this form into our cost function and try to minimize with respect to these two functions. I don't want to give all the details because I want to save some time. I mean, basically, we differentiate with respect to the both functions in one that is ordinary calculus, another one is calculus of variation. Anyway, and we cover the well-known solution. It's nothing fancy, and it's not any more efficient than solving Navier-Stokes for this example. So this raises the question: why a minimization principle is fit? Okay. There are several cases we can discuss at the end, but this is my own motivation as someone interested in reduced order modeling. As an engineer, I really don't care about all the flow details down to the Kolmogorov length scale. I really don't care about this. I care about global quantities like lift, drag, separation point, these kind of quantities. So I'm very happy with the reduced order model that doesn't give me all the details, but give me some of these quantities with good approximation. So if you start with a approximation for your velocity field with some unknown parameters, so you parameterize your velocity field with parameters quite freely, do whatever you like. So I'm happy with this parameterization as a user. All what I need is just the values of these parameters or their time variation, their dynamics. Navier-Stokes as a partial differential equation, we can't focus on the dynamics of few parameters. It's like take it all or leave it all. It gives you the flow details down to the Kolmogorov length scale if you understand Navier-Stokes, so you're doing DNS. If you Want to do averaging, then you're solving another equation. You're solving grads. It's not Navier-Stokes. It's a different equation, right? So Navier-Stokes unfortunately gave you all the details, and which is sometimes good, right? But unfortunately, it doesn't do it for free. It's too demanding to the extent that there is no supercomputer on the entire planet that can solve Navier-Stokes on an actual airplane. It's too demanding.
Is this a Delaunay match or something?
I don't know. Someone give it to me. I'm not an expert in computation. No, I think we use this mission in one of our RANS simulations. And on the other hand, if you have a minimization principle, that's straightforward. You plug this form into your cost function. The result is a cost function that is function of the parameters. The rest is easy. Just minimize with respect to your parameters. If this parameterization is poor, make it richer, add more parameters. Okay, so it will allow you to control the amount of flow physics that you want to see. Okay, so actually, it reminds me of what Lagrange said. I mean, when Euler developed his equations, the famous Euler equations, Lagrange made this comment. He said, by the discovery of Euler, the whole mechanics of fluids was reduced to a matter of mathematical analysis alone. It's like mechanics-wise, it's done because we have the equation of motion. That's done. But all what remains is to solve it mathematically. Okay. Now the situation is reversed. Why? Because the mathematical solution may be simple, particularly if these are few. It's just minimized, and I mean, you can get it easily with the computational power that we have nowadays. But the real challenge is here, actually, how to propose a form that captures the physics that you want to see. Okay. Anyway, let's go back to our problem that has been waiting for a long time. This is the classical theory of lift. I know already the velocity field everywhere, and the theory is actually giving me a nice parameterization. There is only one unknown parameter down, right? So I'm going to call my cost function that nature minimizes at every instant in time. And because this is steady, so I don't have time variation. And I have a means to account for viscosity, but for a moment, I'm going to cross it myself. I'm going to assume that my fluid is ideal, no viscosity. So now my cost is simply, curvature, because there are no applied forces. So this is curvature, and I integrate over a space. I plug this here, I integrate over a space. The result is a fourth order polynomial in gamma. So really high school calculus, nothing fancy. And let's try it for the problem where we already know the solution, a sharp edge therefore. Here is the cost function versus gamma at different angles of attack. At each angle of attack, there is a unique gamma that minimizes curvature. And all these minimizers, they coincide with Kutter's values for this case of a sharp edge foil. So we happily recover the Kutter condition as a special case. Special case of this non-viscous theory. Okay.
Again, those curves are differently. Okay, so alpha is
The angle of attack. Yes. Yeah.
Okay.
Yes. So, but this theory now doesn't care whether I have sharp edge or not. So for the first time, I can consider a family of shapes, smooth shapes, parameterized by this parameter d. D equals 0 is the blue sharp edge airfoil. D equal 1 is the green circular cylinder. In between, I have a family of shapes with smooth trailing edge to which the Kutter condition is not even applicable. So here is the contours of our cost function, curvature, say, or pressure gradient, in the gamma D space. And the yellow curve is the minimizing gamma star, normalized by gamma Kutter. For D, for a particular value of D, give me any value of D, this means a specific shape. For this specific shape, we know that we have infinitely many gammas, but nature chooses only one, the one that minimizes curvature in the language of Hertz. And for D equal 1, this is a green circular cylinder. The minimizing gamma is 0, recovering the well-known fact that circular cylinder is non-lifting. But interestingly, this was not only for circular cylinder. If you tried any symmetric shape, flat plate or an ellipse, purely symmetric, fore, aft, up and down, you will get a minimizing gamma that is 0, which confirms the experimental results of the Caltech folks. They did it also on symmetric shapes. So a symmetric shape in an ideal fluid is non-lifting. But now if you go all the way here to a sharp edge airfoil, we recover the Kutter condition in the limit, which means that the Kutter condition cannot be viscous condition because now it's a special case of an inviscid theory, so it cannot be viscous on its own. So yeah, that's it. Because as you know, this is taught in all undergrad school. I mean, the Kotte conditions. So it created some debate in the community. And then Aerospace America, the magazine, they interviewed Dr. Paul Bevilacqua and myself. Paul is chief engineer of F-35, chief engineer in Lockheed Martin, who built the F-35.
Did you try in the non-ideal case to take non-symmetric shapes with the minimizing gradient of the pressure?
Not non-symmetric shape.
Yeah.
Yes.
Right.
Yeah.
What
I
did you
can
get?
show it to you. Yeah, I'll show it to you. Yeah. So they had a nice article that says with a fancy title. You think you know lift? Better read this. That's if you're interested in this problem, you can read it more. Also, I'd like to say, this is probably my last slide. I'd like to say that this topic has a very rich history. This is, I always move this book, and it wasn't like, it was like this. But then with all troubles, it became, so I had it now as in nice shape. This is a 550 pages book written by a sociologist. David Bloor is a sociologist, about the theory, the history of the classical theory of the lift. Because you know, at the beginning, the Wright brothers, there was no theory, and airplanes were deemed you know, dangerous for military applications. So right before World War I, between England and Germany, there was a mathematical war. Who will arrive at the theory of lift first, because it will help them develop airplanes. So David Bloor is telling this super interesting story, and how the German won the mathematical war, because now in schools we mention names like Prandtl and Kotte, right? So their theory is the dominant theory. They won the mathematical war, and he's talking why you know, why their level of training helped them to get at the right theory. I'm giving a talk on Friday about the history and stuff. I may be able to have some time to touch a little bit on this, but if you're interested, I summarize this book in a bit of detail in 2-part lectures. I put them online under this fancy title, A Mathematical War in the Background of the Great War, if you're interested. I'll skip what's next. If you have questions, we can come back to it. And these are the conclusions. The magnitude of the pressure gradient over the domain must be minimum at every instant in time. And the opinion or curvature is the quantity that nature seemed to minimize in a nice and attached airfoil problem. Using these tools, we developed the variational theory of aerodynamics that generalized Kotte. Most importantly, it's unlike Kotte, it's derived from first principles in mechanics. And it's applicable for arbitrary shapes, not only with sharp trailing edges. And it implies that the Kotte condition doesn't seem to be viscous condition. It's just a momentum conservation. I'd like to thank, of course, my group and the first author of the first paper, Scody, PhD candidate in our group. And thank you so much. Any questions?
I have a very simple question. Consider this non-singular shape. You could still take Navier-Stokes equation and try to tend viscosity to 0. What would you arrive at? You would arrive at the wrong solution.
No, that's a very good question. The issue is that when you take viscosity to 0, you have very high Reynolds number, and we cannot solve Navier-Stokes numerically at very high Reynolds number. So unfortunately, we cannot do that. But we did something that might be satisfying, and actually goes back to your question, which is this is ahead in the slide. So we didn't solve Navier-Stokes, but we solved rands. So we said, okay, here is an airfoil shape at small angle of attack, 2 degrees and 4 degrees. The flow is attached. The flow is nice. We expect the trends will perform well. It actually gives nice results in comparison to reality. So we compare against trends. So let's see what is this. This is our cost function normalized versus gamma at different angles of attack. Black are our minimizing values. And the cyan are the rands computations, which are not Navier-Stokes, but should be close enough, hopefully. The pink ones are, if you say, look at this doesn't, if you put the hat of a practical engineer and say, look at this doesn't seem to be too far away from a sharp. I'll consider it to be sharp and apply the Cotta condition anyway. Because if I don't have this minimizing theory, the only way is to apply the Cotta condition. So let me apply the Cotta condition. If you insist to apply the Cotta condition, this is what you're gonna get anyway, the value of gamma. So as you can see, so even as small as alpha equals 2 degrees, first of all, at all alphas, we are closer to Rands than Kuttas. And even at alpha equal 2 degrees, very small angle of attack. And this is not too far away from a sharp edge. You know, Kutta is quite off.
But you had finite viscosity, right? You
I'm
didn't tend it to zero. I mean, this
one is
not zero viscosity.
yes,
It's fine.
yeah. We
So
can,
maybe when it tended to zero, you will get.
that's what we believe, but we didn't prove it yet. Yeah.
So there is nothing wrong in understanding the correct ideal fluid as a limit of viscosity going to zero.
Oh yeah, that's actually what I'm trying to advocate for, but because some people think that it's not true. Yeah, so that's
I definitely think it is.
yeah, I agree with you. That's my fight now with some people. But anyway,
I wanted to tell you that.
Please.
This is something which I developed in one of the papers of mine recently. I considered the singular solution of Euler, like the vortex line or vortex sheet. And then if you really tend viscosity to zero and solve in a thin layer near that singularity, because it's resolved by the Navier-Stokes solution. So if you do that, you will arrive at certain boundary conditions for Euler to make it. So it's far away from the sheet or vortex line, you have Euler. In the small vicinity, like boundary layer, you have Navier-Stokes. You can solve them and match.
yes.
And that gives missing boundary condition for Euler, which gives unique solution.
Interesting.
So, and moreover, if you compute the Hamiltonian like you do, integral of V squared,
Yes,
there
yes.
are anomalous terms.
Yes.
In the Hamiltonian, if you consider the contribution to the Hamiltonian of integral V squared from small vicinity of vortex line, for example, there is a logarithmically divergent term which doesn't go away when this goes.
Yes.
So
Yes.
my philosophy, which is very close to your philosophy, that if you indeed treat ideal fluid as a limit of the viscous fluid, then you'll get anomalous terms in the Hamiltonian. And the anomalous terms in the dissipation are very well known. They were discovered by Burgers, right?
Yep.
So if you have infinitely thin line and resolve it by means of the Navier-Stokes, you will get a finite result for the dissipation, because viscosity cancels, right? Dissipation is viscosity times integral of omega squared, integral of omega squared diverges. At nu going to zero, it cancels. So there is this finite anomalous dissipation, and there are similar things in the Hamiltonian. What you're considering is minimum Hamiltonian. What I'm saying
Yes.
that for the vortex line, there are finite, actually not finite, logarithmically divergent techniques. So I'm saying that actually Euler Hamiltonian doesn't exist if you consider it as a limit. There are terms which are singular.
Yes.
And that is for a very singular case, for a vortex line. But for the vortex sheet, they are not so singular. It's square root.
Yes.
So what I'm trying to say is that, in my view, kind of common sense says that since there is always some viscosity, the correct definition of ideal fluid is a limit, and if that limit is anomalous, so be it. We don't want to take the value at zero if there is a limit, which is physically.
Yeah, I totally agree, and I'm also looking forward.
I will send you
please,
that
read this paper. Yeah. Oh, thank you.
Again, now back to this picture. So this is what is here the Reynolds number?
Okay, so
like
our
la-
theory is
ARR.
infinite. Our theory is infinite, right? I mean, it's ideal.
Yeah, that's what your theory. There's no
Yes,
hope.
and also Kutta. But here, if I remember correctly, was around 1 million, half a million. Yeah, very large.
But trans is averaging time of the Navier-Stokes.
Yes.
Yeah.
So your results are consistent with the
Yes.
correct definition as a limit.
Yeah. That's what we believe.
Like people when they talk about this Kutta condition, they think about it as determining gamma for the viscous problem or determining gamma for the
They
inviscous problem.
they believe that ideal fluid should not be lifting. So they believe No, not everyone in the community, but really a big portion of the community, they believe that ideal fluids are not lifting. In this particular case of an airfoil lifting airfoil, they are not the limit of Navier-Stokes. This is what they believe. And the Kutta condition is helps us to get good value for the lift because it's coming from physical observation and reality, and reality is viscous, so the Kutta condition is viscous. It's as if you're providing an Euler solution with a viscous boundary condition kind of thing. They say that the Kutta condition takes account of viscosity in an implicit way. That's the.
But now back to this. Now, if you take alpha equals 0 here.
They will coincide. Those two will coincide.
Yeah, but then
Because
it would be
it's
0.
zero left.
No,
Yes,
no, but
it will
for
be zero
alpha
left.
equals 0,
Zero left. This is a symmetrical force. It will be zero left. So Kutta and us and Rands will coincide. Yes.
okay. So then you take gamma equals 0 for the symmetric case. You,
It's zero,
you
yes,
take
zero.
gamma equals 0 and 0 left.
Yes.
So if the limit when viscosity goes to 0 isn't dependent on the viscosity, that's
Yes.
what it is, right?
That's what we. Yeah.
So,
And-
and that means
I
that,
mean, yeah.
that it's a like spontaneous magnetization of a magnet. It's not because of external field. External field provokes spontaneous magnetization. But the nature, of course, is spontaneous. So you could derive it two ways. You could tend external field to 0, that's like viscosity, or you could find the minimum of the
Yes,
energy.
this is what. Yeah, exactly. And I have, frankly speaking, personally have plenty of evidence, but like for example, let me show you this. Like here is. Yeah, this is what. I mean, which can be understandable from a mathematical perspective. So it is already known. That when you crank viscosity to 0, and use number to infinity, up to our capabilities nowadays, and whether experimental or computational, that the lift is conversion to a limit. Okay. So what if this claim is lift is viscous, this means that once you come here and it goes to really infinity, boom, it jumps down like this. So it's as if the physics is discontinuous in the limit. I mean, it can be, but at least all the evidence that we have is that we have something like it. Yeah, something like it.
But I don't understand that you are putting lift equals 0 there.
Yes, actually, that's also another. That's also another
Yeah.
evidence is that for
Oh yeah. Okay.
for very large units number. I'm sorry, very small units number, very large viscosity. You have the Haley shell kind of thing, and you get something like potential flow with 0 gamma. So
Zero left.
it's actually the opposite. Yeah.
Do you think you can use this to can be used to optimize the form of the wave, maximize the drag, minimize the drag and maximize the.
That's an excellent question, and in fact, that was, as an engineer, that was really my motivation and my shock at the same time. I thought when I grew up as an aeronautical engineer, I thought that we computed lift and drag for all these shapes, and then we picked this airfoil because it's the best. But then I was struggling and I realized that, we cannot even compute lift for all these shapes. It's just this shape that this is the only shape where we can compute lift. And it just happens that this shape is good enough. So with these, now of course we have to see if we even Rands. I mean, if we accept Rands as small angle of attack, and we can do this kind of optimization. But hopefully with these kind of tools, we can do even better. Yes, that's what I really want to do now.
I know as Airbus, they used to do those kind of
Yes,
things,
yes.
but with different approaches. By solving Navier-Stokes.
Probably they do it with
They do
Rands.
it by solving
Yes,
Navier-Stokes.
they do Rands, yeah, they do Rands. Yes.
But maybe with this approach, you can
Because
do it faster.
it's more efficient. So it will give you the capability to have a very large design space. What we can do now is doing it for wind turbines, because wind turbines for airplane. I mean, the current theory that we developed, it doesn't predict the drag. I need some significant amount of force to get drag. Okay, so that's
Which is sometimes more important than lift in some application.
that's exactly for airplanes. Airplane manufacturers, they really don't care about. They believe, okay, we're gonna get the lift anyway. Don't worry. Let's just minimize the drag.
The energy, how
Yes.
much energy you have to spend to
Exactly. Drag is you spend money for the drag. So the theory with its current version, it's not suitable for this. It needs good amount of force. But for wind turbines, the drag goes in the blade structure, and the lift is really the force that gives you the power. So we can design airfoils now for wind turbines application that maximize the lift for, you know, say a given angle of attack or a given thickness or whatever. Yeah. Any other questions?
Other questions?
The only thing which bothers me in your report is the following. I would imagine that singularity, non-monolithic behavior on viscosity goes to zero, like any finite viscosity gives finite result, but exactly zero viscosity gives zero result. That's what they're saying.
That's what they are saying, yes.
Yes. So that would mean that somewhere in your space there is a singularity, infinitely thin boundary layer, which you maybe overlook in your variational solution. If you would solve equations or Navier-Stokes equation exactly, then in the limit of viscosity going to zero, there will be some thin region which is responsible for that.
That's an excellent point, and I thank you. This is a very excellent, this is a really excellent observation. Let me, I skipped one point here, and I'm glad that you came back to it. And, where is that? In the comparison between the two principles. Yes, it's coming, maybe here. Yes, okay. So, and this is actually a very interesting point if we think about it philosophically. So here's the point. This is an example where Lagrangian mechanics and Newtonian mechanics fail to give a unique answer, where Gauss' principle gives a unique answer for the motion acceleration. And it's a very simple example. Look at this. This is a cone, two-dimensional cone, but at 90 degrees, okay? So at any point in the cone, the tangent plane, the tangent space is two-dimensional, is a tangent plane, okay? It's well defined and it's two-dimensional. At this point, we have a singularity. The tangent space drops dimension. So at any point here, I can use Newton's equation or Lagrangian mechanics, Hamilton's principle, to get the equation, to get the acceleration at this point. And also Gauss. At this point, if you use Lagrangian mechanics or Hamilton's principle, you will find yourself divided by zero. There is you cannot get the acceleration from Hamilton's principle and Lagrangian mechanics. And surprising also from Newtonian mechanics, there is some ambiguity. Whereas Gauss philosophically works, because Gauss says the following: where is your applied motion, applied force? If this is your applied force, then you're gonna follow the applied force as close as possible with satisfying your constraints. So it will be simply the projection. So this is a rare example. It's quite rare. It's a rare example in mechanics where Lagrangian mechanics and the Newton's equation fail, whereas Gauss' principle applies, which means that it's a bit more generic than Hamilton's and Newton. I believe that there is something similar going on when we go for Euler equation from 3D to 2D. There's some singularity that makes the tangent space drops dimension, but I don't completely understand. There's something similar. Any other question?
Okay, other questions? So,
Thank
thank
you.
you.
I forgot to ask.
I will send you.
I will.
Okay, let me do it a simple way.
Oh, thank you so much.
Just